So, hi everyone, let me share my screen. Yeah, everything seems okay. Let me start a session on, yeah, let's get started for today. Um, yeah, let me see if everything is fine. Seems okay. So, yeah, 10th session. Good. So now, okay, so welcome all to the 10th session of our live interaction series. Uh, into the course of Applied Numerical Methods, ME97. I am Shrey Sahai Gupta. I am the PMRF teaching assistant. I'm a doctoral student at IISc Bangalore. You can look up my email address if you would ever want to reach me out. Um, yeah. So uh, right now there is no audience as such. Is it better if I wait for a few minutes for people to come in? I guess so. So let's wait till 6:05 and then maybe we can start then. Okay, so let's see. Actually, didn't want to start. My plan for today was to discuss the stability of iterative methods. This was in the continuation of the questions that we were having last time on Scarborough criteria and positive coefficient criteria, and then um, in general stability of iterative methods. Uh, so that is something that I wanted to discuss, but I wanted some audience to be there. But it's okay. Let's switch to something that we were doing before that, up till hoping that someone arrives. So that can be there. Let's say let's today explore, or let's just. I was actually using a lot of matrix mathematical notations here to write things down, but it would be nice to actually visualize these things, especially spectral decomposition as such. So yeah, so let's do that part first. Okay. Uh, right. Now, the correct way to do this thing is, okay, let's use 3D kind of situation. So essentially what you generally have is, well, want a vector to be there. Yeah. So this is not a vector. I will try this. Nope. Okay. Hmm. Okay, so essentially, let me say this is a E1. What is the problem there? Hmm. So yeah, okay. Then I have E3. Um, okay. So these are the vectors that we generally look into, right? That's these are the bases of our these are our X, Y, and Z axis, and this is what our understanding of 3D geometry requires, right? These are the three directions that we need to actually visualize before looking into Euclidean space. Uh, but okay, and then you know that you can always have 2E1 plus 3E2 plus 0.1 E3. Let me reduce this so that this can come in. So you see now any vector can be actually represented by very nice combination of these three vectors, right? And so we have a geometrical picture to two vectors, right? And now suppose there is this other vector, which let's say is 5, 6, and 7. And there is this second vector, and tensors can be understood as an operator which operates on, let's say, the first vector, the purple vector, and then it transforms the purple vector into that gray kind of vector, gray vector. Let me change that color so that, let's say, purple or blue or green. Oh, orange, maybe orange. So now let me do it as minus. So that's some kind of, we can have. Uh, Okay, so you can actually visualize vectors, but the trouble is in visualizing matrices, and this is where matrix decomposition or something that I was discussing, SPD or other kind of decompositions come in. Um, they come in order to if you want to visualize matrices, then matrix decompositions are your go-to way. Okay, now because matrices, if you think about it, it is a linear operator. Just like how you don't have a picture, geometrical picture for addition or subtraction or multiplication. Um, Similarly, transfer function, not transfer functions, tensors will not have a geometrical picture. Um, okay, so now we have some audience. Let me close this a bit before we go ahead. So, hi Apur, how are you?
Yes, sir. Fine, sir. Yes.
Great. Okay, so because I was waiting for some audience today, now that you are there, maybe we can discuss uh, back on what you had, the questions you had, right? Last time we can do that. Let me just quickly close this bit. Uh, Maybe we can just quickly visualize, and maybe we'll continue this kind of tensor, like, right? So, so what do you do? How do you visualize this tensor? Uh, you visualize it as an operation on a vector. So it will still be a function. Uh, so let's say you have some vector v, and then let's say we want to visualize e dyadic product e1 dyadic product e1. So then you would know that if you want to get the transformed vector, then you do this. That's So I don't know if it will have dot products or not. Let me pick dot. This was. I think it must be there. No, try. Is this work? E dot E1. Okay, it works. And then E1. Yeah. So let's visualize V1 first, and then let's see what is going on. Uh, so uh, okay. So if you look at it from V1, right? So first of all, you see that the this tensor, this purple vector, is kind of mapping this purple vector onto the x-axis, and the domain or the size of this vector is, if we do it correctly, then let me close this so that we can see. Actually, it will be exactly zero point 0.2. So because you see zero point 0.2 there, so yeah, it's actually difficult to see it otherwise here at least, but it will be exactly zero point 0.2. And now you can similarly do this kind of thing. So what you'll see is, so we've gotten the same vector at the end of it, right? got the same vector. Now I'll tell you what. This is a tensor in itself. So this operation, what you're seeing is a tensor in itself, and it is called the identity tensor or identity matrix. If yeah. So now you can have other tensors also. Um, and generally a symmetric tensor will, I argue that a geometric symmetric tensor will have this kind of a picture where E1, E2, and E3 will not be necessarily these vectors, but some orthonormal basis. They can well be represented in terms of what do you say? Uh, in terms of E1, E2, and E3, and then you can kind of um, actually see how that's like so for example, let's do one thing. Let's create a pair of orthonormal tensors and see what the matrix comes out or what the tensor will come out, and let's see if it is a symmetric tensor. So let's just quickly do that. So let's say E1, let's rotate this entire thing. So, Apoorv, if you're there, can you generate a different? Can you help me generate a rotated kind of orthonormal basis from E1, E2, E3? Can you tell me some other R1 and R2 and R3 expressions for these three? Maybe E1 by root 2, and let's say E3 is this way. Okay, so now let me close this stuff, right? And this and this and then this. So what you'll see is that E3 I've kept same. Okay, this should be minus. Okay, and this is not correct. Or is it? Yeah, it's not correct. It should be E2 minus E1. So we have to actually ensure that R1 dot R2 gives you R3 and so on. So if you see, I've just rotated the entire coordinate system by 45 degrees. That is what I've done. Right? Maybe I can do this. Just see. And let's do one more round of let's just rotate everything by in third coordinate also maybe. So how do we do that? If we want to rotate everything by say, just give me a second. Yeah. So Apur, what will we do if we want to rotate it in the azimuthal direction, or what can we do? So yeah. So what we can do is rotate it, right? Again, rotating means basically finding out a tensor. What can we do? Can we find? Yeah. So what we can do is let's try T1 is R1, and then you get. Let's say let's for simplicity's sake, let's keep this as our basis only. Okay. So now let's try to see how this tensor will look like. So V dot R1 plus V dot, not this dot, R2, and then V dot R3. Okay, now see how we're getting this, and what is this one? Oh, it's the same. Right, we'll get a identity matrix only, isn't it? Right. We're going to get our identity matrix out of it. Um, so yeah, but now we can actually write this down. So what did we write? We wrote this thing as, yeah, so eigenvectors were 1, 2, and 3, right? So we write it as R1 dyadic product, R2, and so on. Okay, just for some fanciness, let's have 2 and 5 there. Let's just have this also. Okay, fine. So now if I want to find Aij, then I will have to do what? Ei, uh, Ei dot. So Aej. Okay, so let's do this kind of thing. So if we do this, what exactly are we going to get? Ei R1 dot ej, then R1, and so on. Similar thing. Plus 2, this will be R2, this 5, R3. Also, let's write what is R1, R2, R3. R1 is and R3 is, just let me check what R2 is also. Let me just check that. Yeah, E2 minus E1, yes. So E2 minus E1 is it is this. Wait, is this it? No, no, no. Yeah, E2 minus E1. Yeah, this is fine. This is R3. The third one is R3. So now let's calculate A11. What is A11? A11 will be E1 entire thing. Let's just quickly do this. So you see here R1 dot E1. So basically R1 E1 square. Okay. Plus then you have R2 E1, R2 even and R2 even square. Yes, R2 even square. Hmm. And similarly, I think 5 plus R3 even square, right? Okay. Now R1 even is what? R1 even is, and let's also put E1, E2, E3 also, just for the sake of them quickly so that you can calculate it. So R1 even is 1 by root 2, and that's squared. So 1 by 2. Then 2 times of um, R2 E1, so it's 0, and then 5 R3 E1 is also 0. Okay, so A11 is half. What is A221 or A12? So A12 you will see A12 is what? E1 dot R1 E2, R2 E2, and R3 E3. Okay, and then what you're going to get is A21 R1 dot E1, R1 bullet E1, and then multiplied to R1 E2. Okay, and now plus 2 times of R2 E2 and R2 E1. So R2 E2 and R2 E1 plus 5 times of R3 E2, R3 E2 and R3 E1. Okay. Uh, Before I go, like we start calculating every term, let's just also calculate A21. Okay. Let's calculate A21 and we'll see that A21 will be equal to A12. Okay. This is A12. Let's calculate A21 also. So A21 will be, this will be 2, this will be 1. What is it? A21 equals to uh, R1 E1 and R1 E2. Okay, the first term is fine. Then the second term is 2 times R2 E1 and R2 E2. Okay, R2 E1 and R2 E2. And then 5 times uh, R3 E1 and R3 E1 and R3 E2. Okay, now let's just compare R1 E1, R1 E2, R2 E1, R2 E2, R3 E1, R3 E2. See how they match. Okay, and this is essentially because of the property of this dyadic product. Okay, we have not discussed this probably, but you can actually get a feel that if we do this kind of thing, if you keep going through, you will see that this will result in a symmetric matrix. And that is a very strong property of symmetric matrix. That is, as we were discussing some time back, that this leads to that singular value decomposition kind of stuff. You get singular values for a non-square matrix as well. So maybe I'll stop here because I don't want to get into this too, I want to discuss other things today, basically stability of iterative methods. to begin with, because this is something that this was an open question we were discussing last time. Okay, I'll keep coming back to this part. Complete whatever we had left on SVD and stuff. Try to complete it. So, anyways, uh, coming back. So, Apu, a little bit of discussion maybe. Any questions for starters? Any new
No,
questions? Or
I was wondering if you could discuss slightly about PINN because last class you were saying you will be discussing that.
PI Allen?
PINN, so physics informed neural networks.
Oh, okay, okay. PINN. Okay, so n not today. I didn't do that part today. What I have done this stuff was you had a question how Scarborough criteria was kind of derived, right?
Yes, yes.
So maybe we can discuss slightly on that. First of all, actually, uh, slight mistake on my part that we actually didn't discuss the practical problems with solving AX equals to B. So uh, you remember that you mentioned that could we discuss CFD or finite volume methods of solving equations, right? You said finite volume method solver, right? And you said that there we get Scarborough criteria, right? Um, and I kind of just shut it up by saying that at the end of it, you're essentially solving AX equals to B. But when I went back and did it like read things about it properly, I realized this fact that you actually can't solve AX equals to B for like efficiently, especially when you have a large number of elements in your system, which is a finite volume case. So a quick chat GPT search, we could actually discuss this part of it. See, when you're trying to solve AX equals to B using that LU decomposition or Gauss elimination, what essentially the problem is that your computer will run out of space and it will take essentially infinitely long time. Okay, so suppose you have a large number of nodes in your domain, right? So the time complexity it takes to solve AX equals to B uh, is order of n cube. So suppose your number of elements, you have millions of elements sometimes in a 3D simulations, time complexity will be cube of that, and the memory, the amount of storage that you will have to keep is n square. Okay, so that roughly what does that imply is some rough ballpark numbers are that if you have only 100,000 number of nodes, then the storage can will be of roughly of 8 MBs. But if you go to let's say 1 lakh, 1 lakh or 10 100,000 nodes, basically your storage goes to 80 GBs. You see how fast it is scaling up, and the number of amount of time it will take is 10 to the power 15 flops. Okay, months or years on a supercomputer. That's very expensive, right? You can't solve AX equals to B by our LU decomposition when this size of A increases. And this is something that I had skipped. I didn't look into it too much essentially, but then I went back and read about it, and there is a simple strategy which Apoor was mentioning, which was of what we call as iterative solvers. So I think that that is what you meant, right? This iterative solver. So basically, if you would look at it, there are two ways to solve AX equals to B. The first way was our find A inverse B. That is what we are trying to do. But now if I go back and actually this kind of very nicely correlates to what we had discussed in the first session on a glimpse of numerical methods. We had a iterative solver, right? We take a initial guess and we kind of suppose we kind of hope that we by substituting that initial guess into our system of equations, we kind of get closer to our to a true solution. So the second way, this is the direct solver way. Whereas indirect solvers are actually iterative solvers. And what you do is you start with the initial guess. Okay. And what you do is you keep on increasing. You start with the initial guess, first of all. And just like how we had tried to solve for the square root of a number, we do this. X k plus 1. Uh, what do you what do you hope for it? Basically, you try to find this uh, as a function of a, x, k, and p. And so essentially, what you're doing is you're kind of substituting a x naught and then minus b kind of thing to get xk. So there are actually different ways to do this. And as I think you guys are aware of Gauss-Seidel. So sir has explicitly discussed Gauss-Seidel and Jacobi's method, or is it something that you read on your own?
Yes, it has been discussed.
It has been discussed, right?
Yes, sir.
So so this part of this how ax equals to become b, ax equals to b becomes very expensive, or it has also been discussed well, right?
Yes, sir.
Okay, great. So now, so basically what you do is, for Jacobi's method, you break A into, basically you write A as L plus D plus U. And then what you say is that L in Jacobi's, in Jacobi's method, what you say is, uh, L plus D of xk equals to B minus, basically xk plus 1 is B minus U xk. So have you seen this kind of expression before?
Yes, LDO decomposition, right? This is,
This is not LDU.
yeah.
LDU is LDU is L times D times U,
Yes, yes.
but we are kind of L plus D plus U. So this is not LDU. Okay, so maybe just quickly, this is not a very fancy thing. Essentially, at the end of it, what you have is for every node, you have one equation, which is coming from trying to uh, uh, approximate the governing equation at that point. And what you basically get, suppose your number of points is so say, let's say J defines the nodes, right? J goes from 0 to n or 1 to n, and then AJ is the jth node, or so basically, yeah, so AJ xj plus summation j is not equal to, I don't know what is this, not equal to p, and then you will have AP, let's say, or yeah, AP xp, and then you will have what? AJ xj equals to BP. Okay, and if you think about it, uh, you have, let's say this is APP, yeah, APP and then AP comma J. So for the pth node, when you write the governing equation, you will have coefficients for all other x, or every coefficient, be it zero or some other finite value. Essentially, you are going to, this is also AX equals to B, right? So now Jacobi's method, what does it do? It puts all so basically it finds what it will do is, let's say we will have a1 1x1 plus a2. Let's say this is the system of equations we are trying to solve. A13 x3 is b1. So let's say quickly, let's say this is Jacobi's method. Okay, so and the system of equation is this. So b3 and then b2, and then this is 2, this is 3, this is 3, this is 2, and this is right. So now what do you do in Jacobi's method? In the first iteration, you find x1 as writing as b1 minus a12 x2 plus a13 um, x3 and so on. So essentially, if you look at it, and this is a11. Actually, in this kind of format, if you see a13, or let me again just quickly write this also so that this becomes clear to you. P2 minus A11, A21, sorry, A21, X1 plus A23, X3, and just simply another kind of, this will be A3, this will be, yeah, this will be X2, this will be 232, this will be 31, right? Just one more thing. That's a 0. So essentially, if yeah, tab is I think. Okay, so this is there, right? Now, if you see this, what you will notice is
Third equation has to be A33x3 on the left side.
A33. Yeah, right. A33x3. Then this is also red, and this is green. So now what you will see is the green terms are terms in the left hand, in the lower diagonal part of the matrix. So A21, A31, A32. Whereas A21, A13, A12, A13, and A23 are like the upper part of the matrix. So in the Jacobi's method, actually, I wrote it incorrectly. This is the solution scheme. So basically, there is a lower diagonal matrix and there's a upper diagonal matrix. You basically separate these columns, and this is the solution scheme in Jacobi's method. Let me write that. In the Gauss-Seidel method, I'm assuming that has been discussed, so I'll just quickly write it out. Let's see if I can write it correctly this time. It's L plus D, L plus D xk. So now if sir has discussed that part to you, maybe you can tell me if I have written this incorrectly or correctly. What does Gauss seidel do? Yeah, there's one more important thing that I have missed writing here. Let's also write the iteration number in xk. So let's say this is x1, 1, this is x1, 2, this is x1, 3. But here, all these values are from the 0th iteration. Okay. In Jacobi's method, we don't update our values. We update the entire set of the values after traversing through all the equations. 0, comma 3. So basically, this notation that I've written here is x k comma j, right? K is the iteration number, j is the node number, nth node. So for you, did it get clear or you still have that paragraph doubt? Let me ask that as well. So kth iteration. Okay, so this is the Jacobi's method, right? We update all our guesses in one go. In Gauss seidel, the approach is a little different. In Gauss seidel, so Apoorv, did it your doubt about did you find some idea about that Scarborough criteria?
Uh,
I didn't understand if you said something. Anyways, so what you basically do in Gauss seidel is you keep updating. Yeah, you're saying something. Probably not. So,
Scarborough criteria say it has got to do with this diagonal dominance, something like that.
but did you
The
figure out why it actually said like it can guarantee convergence? That was your question, right?
yes, somewhat. No,
Okay. So now what do you do is here you kind of update the gases as soon as you get an estimate. Okay. And so this is x11 and x12, right? So now this you see the L the lower domain, the lower matrix or the lower diagonal matrix is now associated with xk plus 1 and not just xk, right? So earlier the lower diagonal matrix was associated with xk. Here we will retain L on the left hand side. So in Gauss seidel, the iteration scheme is basically you trying to calculate xk plus 1 is what you're trying to do is essentially this is what we do when we are trying to figure out the solution using iteration schemes, right? This is what we do. L plus D inverse B and then minus L plus D inverse, supposing that L plus D inverse exists, which I like read that it's highly unlikely that you find a non-invertible L plus D kind of scenario in iteration schemes. Okay, so we are not going to like don't have anything to say about that as of now, but these are the two schemes that we kind of use. Okay, fine. So now let's quickly talk about why Scarborough criteria can actually, if met, why will it kind of um, satisfy our convergence criteria. Okay. So let's consider, and I'll tell you, Gauss Seidel is actually the iteration scheme. Scarborough criteria is in regard to. Okay, so it is associated with Gauss Seidel kind of iteration, and yeah, that's it. And still, you see, still we are trying to solve ax equals to b. So don't forget that. So okay, so that is there. So now, okay. Okay, one more thing that we can do is we kind of want a solution which kind of, so the true solution, how would the true solution look like? True solution will be ax equals to b, which implies that L plus dx, let's say true solution will be b minus u x true, right? That is what it is, which implies what? If you subtract this equation, so did you understand why this will happen? Essentially, once convergence is reached, once the true solution is reached, you're not going to move any further. Like your iteration will now be stagnant. It will not get to a new value. It will be coming back to the same value. And so that is what it means to satisfy the set of equations, right? So now if I subtract these two equations, what you're going to get is L plus D times xk plus 1 minus x true is b minus u. So bb gets cancelled. You will have minus u xk minus x true. So quite interesting. Okay, and one more thing that we'll do is we'll call it error. This entire thing we'll call it as error. And this is the kth error at the kth iteration, and this will be the error at k plus 1th iteration. So up till now, is everything fine, Apurv?
Yes, sir.
So first of all, it's quite interesting to see that how B actually kind of just vanishes off, right? Another important thing is, suppose this we would have done it using Jacobi's method. Okay, suppose this was a thing in Jacobi's case. So what would we have gotten there? We would have gotten L plus U here, and D would have stayed on the left hand side. So now what that would have implied that ek plus 1 would be minus d inverse L plus u. And so you see different, and this is okay. Let me write this part also. Minus L plus u inverse L plus d inverse u. So you see different schemes are kind of getting your different convergence scheme, right? Convergence, the way your solution converges is different with depending on your scheme. These two equations kind of signify that. Acha, one more thing. Uh, do you realize that these two equations are kind of representing a dynamic system?
Meaning, sir?
Meaning that uh, suppose we would have done some Euler discretization. Suppose there was basically what I'm trying to say is that these two equations kind of write, we are kind of writing this some function of E. This is what this equation is. Suppose you had a dynamical equation of some sorts. Let's say d by dt is some function of fe. And now we do that Euler discretization. So we know that ek plus 1 minus ek will be f ek plus delta t, and then you can actually take this thing on the other side, and suppose f of ek was linear in ek. So if I do that, then let's say some alpha or kappa, let's say kappa is the proportionality constant there, and you had ek. So essentially what will happen is you would be writing something of this sort. Actually, this is not correct. It has to be some matrix, some tensor or some matrix kind of thing. So maybe some B or K. Then you will have K delta T and then EK. So now you see I unity plus K delta T, and these two matrices are kind of equivalent, right? You see that this is a dynamical system, right?
Yes, sir.
So basically, we're trying to say that how E of K will evolve, and it can very well be represented by a continuous system also, right? And yeah, you're saying something? Okay. So now what I want to kind of just emphasize here is that you can actually figure out that there is a stability kind of scenario can come in. Basically, we know in a dynamical system that there is a stability condition, right? A system is stable if your eigenvalues are, what do you say, negative and so on, right? Isn't it?
Yes, sir.
Uh, so if your eigenvalues are negative, then you write, um, then you say, um, what do you say? Then you say that this is a stable system, and if they are positive, then you say then it is a unstable system. But in the case of in a vector notation, actually, I'll maybe quickly introduce matrix polynomial, this matrix exponential also at this point. In case of a matrix exponential, just open that part. I'm gonna copy this. Yes. So in a matrix kind of thing, if you have x dot of t, right? So x dot is, let's say, some matrix times x, some linear operation, right? This was a discontinuous approach, but in a continuous approach, this is what how it would look like, right? Basically, I'm trying to say E and E, right? Then actually and suppose E of 0 is iota E, or let's not say that. Then essentially your x E of t would be, what would it be? It would be something of, this is a notation which I'm writing now. E of t times t and E of 0. Right, this. Actually, I've used this notation in, this is not the correct way to use. I've used E, right? This is, let me write exponential. E of 0 exponential times t of t, where exponential times t of t is a like it's a matrix. Okay, it is a matrix because you see t is inside the argument of x, this exp. So how does this matrix look like? Let me just give you that also. It looks like I plus t times t plus t, or t times what? Yeah, t t and then t square by 2 factorial, and you get the idea, I guess. Okay. Now, one more thing one more thing is that the eigenvalues of this matrix, so eigenvalues of this matrix will be e to the power lambda of lambda I of t. So what essentially I'm saying is, actually there is a lot of heavy notations that I've induced. Basically, don't get um, don't get overwhelmed by this new X matrix exponential. That's kind of very similar to the scalar exponential that we know of. But the important part is, suppose t has some eigenvalues, right? So E dot equals to TE, the eigenvalues of what do you say? Eigenvalues of your resulting solution will always be, you see here, we either it is positive or negative, this will always be positive. If your lambda I is negative, then also e to the power lambda it will be positive, right? Right? It will be always, it can be very close to zero, or it can be very high, greater than zero, but it will be positive. So in this case, the stability will come from, if basically the stability can be written as that the eigenvalues of matrix exponential um, is what? Eigenvalue of the matrix exponential is less than 1, because then that would imply that lambda is our negative. Does that make sense?
Yes, sir.
Okay, so basically we're trying to say that this thing is the eigenvalues of this thing will be less than 1. Okay. Okay. Anyways, kind of a detour here, but okay, coming back to our Gauss Seidel thing. Mm, yeah. Okay. Mm, L plus D inverse of U. Just give me a second. Just give me a second. Got kind of confused with this notation. It's okay. Yeah. One second. Okay. So now, if I go back to this kind of notation in Gauss Seidel, so this kind of scenario, if I were have to write ek of plus 1, ek plus 1, and then I write it for a pth column, pth element, then I will have a pp, then actually, yeah, BP and then summation of this sum. Put this sum. Where is it? Right? XJ and everything is fine. Yes. Now, yeah. And this BP will go. See, this BP has to go, right? Just like how B went off from this end. And this will be EKJ. Actually, we need to discuss this more properly. This thing. Actually, we need to stop here and just, I want to ask you, is this okay? Are you able to see why? Are you clear what P and J are?
The K and J is fine. I don't understand.
You don't know P what P is?
P, we can like we consider 1 point P, maybe that way.
Everything is okay. What is there any issue there? No, right?
P is probably one.
Yeah, let me write that. P is Pth equation. Or equation for Pth node. Right? So this is because we have a matrix at our hand, we need two iterators to traverse in the entirety of the matrix, right? So P is the first iterator, J is the second iterator. This is the like column, this is the row kind of thing. But is this equation okay with you? That's the important part.
Can you repeat once again, sir? This.
And actually, this will also have some terms. Basically, this will not be just this, right? This will be J less than P. And wait, so L is there. Yeah. And then plus when J is greater than P. Will be here. Essentially, EK plus 1. This is what Gauss Seidel is about, right? Yeah, which part do I need to explain?
Now it's okay, sir. Now it's okay.
Now it's okay. Okay, fine. What else? And what if we do it for Jacobi? How do we write it for Jacobi? For Jacobi, this should be, this will be just J not equal to B, right? What do you think? Right now, basically, now what do you see here is this is still a kind of, what do you say? So basically, this is L times of E is minus, sorry, D times L plus U of EK. This is EK plus 1. Okay, so what do you see here is that basically, again, this is a matrix operation. A vector is being mapped from, let's say, yeah, it is being mapped from one vector. So basically what we are doing is, let me do this also, D inverse. You see, basically here also EK is being mapped to a E, like in the same dimension, in the same space, we are having a matrix operation at the end of it, right? So we can actually think of it in terms of now lengths and vectors and yeah, in that kind of format. So suppose what we'll do is we'll see um, actually what we actually need to realize is introduce that thing. So just give me a second. Yeah, so basically what that means is that whatever this matrix is, right? The eigenvalues of this, as I mentioned, should be less than 1. That's important actually. So this should be less than 1. You see this and this. Only in the limiting case of t tends to delta t, or and delta t also tends to 0, that these two quantities will this will be equal. But in the strict sense, we should not have this, but exponential of t, right? It should be this in the strict sense. And that is why uh, to be precise, it should be this is approximately true. This is also approx, but accurately this is the thing there. Okay. Now what essentially this entire thing has to do is that the eigenvector of this entire thing should be less than 1. All the eigenvalues of uh, the magnitude or the scaling, whichever whatever we are doing, signature the polarity can be negative. Polarity does not matter at as far as long as the magnitude of these eigenvalues of this matrix is less than 1. It does not matter what the polarity is, it's positive or negative. We know the solution is bound to converge. Oh, something happened. Yeah, it's okay. So yeah, right now um, okay, so that's there. But what else can we do? Okay, we can also take norm, right? At this point of time, we can go ahead and take norm. So let me just take norm of this entire thing, both sides, right? So what I'll write is actually, and I can take minus, I can just take away minus sign uh there, right? Now, what else can I do? Can we move forward with this? Let me think. Actually, actually more convenient formation would be this to actually see how Scarborough criteria will come. So we actually divide this thing with A1 by AP also. That is important. This is an important step to make. Okay, this is okay. And now let's take norm. So now if we take norm, so whatever we are doing is kind of identical. Okay, it's so this expression, whatever I said, the magnitude should be small. In some sense, we are kind of making progress in the same direction. Now let's take norms on both sides. Okay, and again norms on both sides. we can actually absorb the minus sign, and at this point we will break the right hand side into using the inequality that mod of AB is less than mod of A into mod of B, right? So now this becomes, this will be less. Now the equality will come. So that is important. Inequality will come. And inequality will break for every term if you would like. Okay. Now, yeah. Um, so that is there. What else? What's the next step? How do we derive it? Hmm. Let me take this to the next screen. Okay. Acha, just Apur, now I told you, right? I told you how this is a matrix. This is still a matrix, right? And whatever we have done is we have basically taken for the sorry, this is still a vector, not a matrix. This is still a vector, right? This and this is still a vector because K and P. So K is the iteration, but P is the
Points.
pth component, right? So essentially, what this does this say? This is basically saying what? This is basically saying max of um, norm of E K, mm, comma P. Actually, K plus 1 is less than this entire thing. Basically, what I'm saying is, um, suppose EK will be something of this sort. EK2 and so on. And then mod of EK, basically the way we have taken our mods, right? And so on. Now you tell me if we satisfy this for the maximum of the mod of these entries, will other entries will also get satisfied? So what I'm saying is that um, max of P norm of PKP PK plus 1 P, if we satisfy this, then all for all it will get satisfied. This is what I'm trying to say. Let me write this. Max of actually this is a leap that we are kind of taking. Or we just take this, yeah. This is also okay. This is actually more intuitive. Let me think. Have I written this note? Have I written this down correctly or wrong? Incorrectly. So because these are positive numbers, we can actually write this. Is this okay? This part. Again, the proof is a little like I'm not done this proof properly multiple times. That's why it's a little hazy, but still the proof is fine if we do it strictly speaking. But at least, do you get this? Will this be okay?
Yes, almost, almost.
That makes sense, right?
Yes, sir, quite.
No, but does this make sense, or it still does not make sense, or somewhere
Yes,
you're having issues?
inequality and all those are there. Only how this maximum thing came.
Okay, so why does this maximum thing come? See, this is a summation, right?
Yes, sir.
If we can satisfy, um, wait, let me think. If we can satisfy this over, hmm, hmm. Okay, this is, let's say this is wrong. Okay, suppose I want to find what is the maximum component of this vector. This vector, what is the maximum component of this vector? Okay, I take maximum on both sides. Okay, this is what I'm doing. I'll take maximum, the highest component of this, like the largest component of the vectors on the both sides. Okay, so then same thing, and then you write this part of it. Okay, a little tricky. I'm also getting a little confused, I think. Hmm. Uh, and the way you do it is basically this max operator will now break. Again, it will break into this component. So how it will break? Actually, this identity will hold. Will this identity hold? Can I write this? Let's forget about this. Can I write this? This is still fine, right?
Yes, sir.
Right? This is still fine. Now, uh, max of this thing will be lower than this. And now this RHS will be lower than this, right? This will be, a little. Actually, I didn't want to introduce. Uh, see the this entire proof gets that the proof comes from the notation of matrix norm induced by vector norm. Okay, this is something which you can actually read about. And basically what it is it's a, so basically you know about the norm in sort of this. So what do you know is L square norm, I guess, right? X is, you know about SQRT and then square terms and so on, right? You have x1 square and so on. There are
Yes.
other norms also. Okay. Okay. There is this norm called as matrix norm by induced by vector norm. And it's a norm of the matrix. It's defined like this. It's a matrix norm indeed. It's defined like this. Check how is it defined. Yeah. There is something called as superium. Uh, didn't want to get into this, but anyways, just kind of overwhelming you. That's it. Uh, yeah, this is something called as matrix norm induced by vector norm, but we don't need to get into it because essentially this matrix norm is kind of dealing with this stuff only. And now because I don't have a proof, well-defined proof, I would have to write it because it's the proofs are generally given in this matrix norm kind of situation, but it essentially comes from this max kind of stuff. So there is this norm called as a infinity norm. And it is actually defined like this. How is it defined? Infinity norm is defined like, mm, yeah, it is defined like this. Max of P summation. Okay, and now you can kind of see that this will be some matrix norm stuff, right? But anyways, I didn't want to get into it because this is not the way I would like to prove it to a undergrad class, right? Um, but anyways, it's a little tricky, but let's see. Let's quickly see this properly. Okay, so what's going on here? Basically, this thing will hold. Now, the RHS will be lower than the this entire thing also because now whatever we are what are we saying is that there's a summation, right? There's a summation of positive terms. Then we know, what do we know? We know that A1 x1 plus A2 x2 will be lower than A1 x1 A1 plus A2 x2 given x2 is greater than x1. That's the logic. That's why we can separate them out. Um, Now, what does this imply? This identity. It implies that the maximum component of the error, right, will always be lower than this term, this entire thing, times the whatever. Like, so the maximum component in your error will keep getting multiplied or will always be lower than this identity, this coefficient, right? There is this coefficient coming. This is where the Scarborough criteria comes in. So, and there is a kind of a high leap that we have taken from going from this to just this, in saying that if this is less than 1, then we are definitely sure that our error will keep on reducing. Do you get the reasoning there at least? There? You there?
Yes, sir. This thing.
Right? So maximum comp or the largest component of the error keeps will always be lower than will so basically it will keep on decreasing, or it will keep getting multiplied, or it will always be lower than this coefficient term, this term, uh, times this. So now what essentially we are saying, if this is less than 1, then max of this entire thing will be less than 1, and that is why that in that case this will keep on converging. So this is the proof for Scarborough criteria. A little convoluted, I must say, but yeah, this is the reasoning there. So any questions as such, or did it just not make sense? It was not useful any, like it was still Scarborough criteria was unintuitive, and this explanation was also unintuitive. Was
I'll
that
have
the
to
case?
I'll have to go through this again. Actually,
Okay, would you like me to go through this once more?
no, sir. No, sir.
No. Okay. Maybe I can just refer to, well, it is not there in that book. So yeah, maybe you can just ask Chat GPT once, or read about this. Maybe let's see if there is something. Yeah, so maybe you can go through this once, and maybe if you have questions, we can come back to this again. Essentially, what we are saying is that your error will have a lot of components, right? P components, or N components to be precise. The highest component of that error will keep on, there will be a relation to the highest component, right? Uh, we realize that by simple reasoning, your highest component will keep getting multiplied by this fraction, or at least it will keep on be lower than this expression, this coefficient times the maximum component. Now, if this is less than 1, we are certain that this maximum component will keep on decreasing, and that's why the solution will converge. But again, because this is not an exhaustive proof, this is not a Scarborough criteria is not a sufficient criteria. That's why a lot of iteration schemes, or a lot of methods, or lot of situations, Scarborough criteria gets unsatisfied, or it's not satisfied, and still you get convergence. So it's a conservative criteria. Okay. Anyways, let me quickly take a small break. I'll come back in 2-3 minutes, and we'll continue a little bit on the stability of iterative methods, a little bit on it, little bit, let's see, on von Neumann or stuff. Basically, we'll talk about the eigenvalues of this thing. Let's see. Yeah. Okay. Okay. So maybe I'll just demonstrate the fact that the eigenvalues of this has to be less than 1 to mm, right. What should we do? How much time do we have? We have 20 minutes. Can we do a few things? Let's start. I'm still audible, right? Check.
Yes, sir.
Yeah. I'll just quickly show to you that see iterative schemes actually both your governing equation or the PDE and your iteration scheme matters. So let's see. So we have a system of equations. We're going to use Jacobi's iteration and then Gauss Seidel to see how do we uh, do on the solution. Import numpy. What else to import? Import matplotlib, I guess. Okay, now let's go ahead. I have a matrix at my hand. Okay, 5, 2, 2, 2 minus 6, 3, and 1, 2, 7. And B is what? Yeah, B is 9 minus 1 and 10. 9 minus 1 and 10. And let's do this. Okay, let's find the solution to this. What happened? np.lib algebra dot solve a comma b. Let's find what is the solution. 1 comma 1 comma 1, right? This is the solution to ax equals to b. But now let's use Jacobi's method. Jacobi's definition. Jacobi x. So basically what we'll do is we'll find xk plus 1. So we have xi or xk. Let's find xk plus 1. So what is xk plus 1? Because we have three equations at our end, let's use this. X. So x0 or x1 is v0 minus a01 into xk1 minus a0 comma 2 into xk2. x2 is b of 1 minus a of 1 comma 1. Sorry, a of 1 comma 0. do x k of 0 as a of, and then yeah, you will also have this thing. Not to forget that a of 0 comma 0, right? Even in this case. Please tell me if you're able to just see what, if you're able to just see that this will, I'm writing the right thing, right? You can just tell me that and just tell me that.
Actually, it's very small. Uh,
Oh, it's very small, huh? Sorry, man. Come on, let me. How is this?
Now it's better. Yes.
Okay. Just tell me if I'm writing it correctly or not. 2 comma 0. This will be 2 comma 1 makes 1. Yeah. This is the Jacobi's method, right?
Yes, sir.
Let's see if this works for us. For I in x0, let's take the initial condition to be 0 comma 0 comma 0 for I in range. Let's say 10. If print x0 equals to Jacobi x0, print x0. Let's see. Okay. Let's see if we reach the steady state or not. We do, I guess. In 20 iterations, we will, I guess. It's close to 1, 1, 1, 1, 1, right? Okay. Now, so this one is okay. Maybe I'll write Gauss Seidel also at this point. Now, Gauss Seidel is actually quite easy to write. Here, what you do is you don't do xk equals to 1, you just write x1. And here you write x1 and you write x2. The Gauss Seidel approach. Let me see if we traverse Gauss Seidel, does this work or what is it? See that. I think it, let's see. Since there, Gauss Seidel works for this case also, right? You go to, wait, not x0 is 0, 0. Right, so we are kind of traversing. So this is large enough, right? We'll reduce this a little bit. So both of them are going to 1. These are the two approaches. Now I'll slightly change the matrix A. Basically, what I'll do is, yeah, I'll change these two columns. 7 to 1. Just my simple change I have made. Let's see what happens with the two approaches. The solution still remains 1 comma 1 comma 1. Okay. Now with Gauss Seidel, see we are diverging. In 20 iterations, we are very far. But with Gauss Seidel also we are bad, huh? No, that should not be that. That should not be the case. Wait. That means I've made some error.
Is the Scarborough criteria satisfied?
Let's check. That's a that's a good question. So what is the Scarborough criteria? You'll have to write three criteria, three numbers, right? So Scarborough criteria is, so basically 5 to 2, 5 to 2, 2 -6 and 3, 1, 2, and 7, right? So then the Scarborough criteria will be 4 by 5.
Third row it is not satisfied, right?
This for this case, yes, yes. In this case, it will in the first case it is not satisfied. Yes. No, no, in this case only it is not satisfied. 4 by 5, then 5 by 6, and then as you mentioned, 9. It's 9, right? So it's unsatisfied. But I think it should work for Gauss Seidel. I'm not sure why it didn't work for Gauss Seidel. I have written it incorrectly or something. Let me check. About as far as I am informed, this will work. Yeah, maybe this is about maybe both of them will not work. Is that the case? Gauss Seidel does not work, huh? Probably it would not work. But let's see why this thing does not work. As I mentioned, this has to do something with the eigenvalues of our matrix. So in either of the case, let's calculate L, D, and U. What is L? And P dot array. 0 comma 0 comma uh, 0. Then you have a of 1 comma 0, 0 comma 0. Then you have a of 1, 2 comma 0, and a of 2 comma 1 and 0. Let's see what L is. Right. Let's also calculate D of 0 comma 0. Five, yeah. And then just let's calculate Q also. Right. So this is the case, right? LDU. Now, for Jacobi's, what had we written down? For the Jacobi, this is no, this is for the Gauss seidel and this is for the Jacobi. Let's find out these matrices, okay? So Jacobi, uh, T Jacobi is minus L plus D NP dot inverse into U. What is TJ? What is wrong? NP dot inverse is not defined. Oh, we have to use SciPy. What? SciPy dot linear algebra as LG. Yeah, interesting. And then we'll also use, there is also eigenvalue, right? MPy dot L. Okay. D inverse L plus U, sorry. What have I done? D inverse L plus U. It's really wrong. Minus D inverse L plus U. Minus D inverse. What is D? Is D invertible? D is invertible. And L plus U is what? Yeah. Oh, I'm doing this in two. That's why. Right. So let's calculate, just find D. Okay. And then we'll also use, that's the issue. And then the other one is L plus T. And then the other one is L plus T inverse U. Yeah, this one is also okay. Oh, it's T comma V. That's why. Okay. And this one is what? Okay. So in both cases, you will see that, see, one of the highest eigenvalue, the eigenvalue with the highest magnitude is greater than 2 in both cases. In both Jacobi and both Jacobi and Gauss Seidel, you will see that the eigenvalues are greater than 2. But if I just go back to this one where your Scarborough criteria was getting matched, now let's see what are the eigenvalues. Less than 1, and in this case also, I think less than 1. So actually, it matters what your eigenvalues are of these matrices. Okay, so this is what is there. I think, yeah. Um, Eigenvalues of this thing are, yes, correct. So this is what I wanted to just show. What else? Is there a is there a scheme where this we can figure out this solution? Yeah, I think no. We'll have to see. I'll have to see if there is some scheme where we can kind of satisfy this. Probably not. If I start close to one, then also it diverges. So that's a problem there. Anyways, so this is what I wanted to just show. Maybe I'll complete this next time. Discuss how there is a better way. So this will again become prohibitively expensive to figure out if your solution scheme is stable or not. If you are at the end of it trying to find eigenvalues, as I mentioned, finding eigenvalues of a matrix is similar to finding AX equals to B. So there is another way. There is a classical way called as von Neumann analysis or Fourier decomposition of error to figure out if your solution scheme is stable or not. And it has to do something. So basically, what we are doing, we basically here, what we were interested in was maximum of magnitude of eigenvalues. Okay, and this is termed as spectral radius. Okay, in numerical methods text, it is called as spectral radius, I guess. Let me just quickly check what it is called. Yeah, spectral radius of convergence. Okay, maybe you can read about it a little bit, and maybe next time then we can discuss it. We can continue our discussion on the slides. Okay, then close. If you have some questions, you can discuss that, or otherwise we can close.
No questions, sir.
Thank you. Yeah, thank you.
Okay, sir.